the circulation on the airfoil is related to the lift through the Joukowski law that the section lift is equal to rho v infinity times gamma. So in the previous video we saw the expression for gamma, and if we just plug that in here, what we get for the lift is 4 pi rho v infinity squared times the square root of r squared minus eta naught squared times the sine of alpha plus eta naught times the cosine of alpha. Okay, so that's the section lift. Usually though, we're interested in a lift coefficient. So the lift coefficient is simply, the section lift coefficient is the lift per unit span over 1/2 rho v infinity squared times the chord. And for the chord, what we're going to use is z trailing edge minus z leading edge. So we talked about this when we developed the geometry of the airfoil, of the Joukowski airfoil. That's what we call the chord. Okay, zt minus zl, and zt, by the way, zt we found was equal to 2. So the trailing edge is c naught plus the square root of r squared minus eta naught squared. And z leading edge we found was at minus 2 r squared minus eta naught squared plus c naught squared over the square root of r squared minus eta naught squared minus c naught. Okay, so notice that both of these are real numbers. They're both real, and we can subtract the 2 then to get the chord. Okay, so if we plug that in, so if we take this expression for lift and plug it in and divide it by all the stuff there in the denominator, what we get is let's see, we get 2 pi times sine alpha plus eta naught times the cosine of alpha divided by the square root of r squared minus eta naught squared, and then that whole thing divided by 1 plus c naught over the square root of r squared minus eta naught squared minus c naught. Okay, so that's what we get for our lift coefficient, and I'd like to just rearrange that so we have some CL, the two-dimensional lift coefficient is equal to CL alpha times a first term there, which is going to be sine alpha plus something else times cosine alpha. Okay, and so what we would get if we just rearrange this is that CL alpha tilde, the lift slope, is equal to, we have the 2 pi out front here, and then actually this is just a constant down here. It's independent of alpha. We've got the sine alpha and the cosine alpha there, so we can pull this all out front. And so the lift slope then is equal to 2 pi over 1 plus c naught over square root of r squared minus eta naught squared minus c naught. Okay, so that's what we're going to call CL alpha. That's out front there. And then inside, we're going to actually call this term here. So we've got this sine alpha term right there. We've moved this denominator out front. We've got sine alpha, and then we just have some constant here times the cosine of alpha. Okay, so that constant we're going to call that the tangent of alpha L0. And usually we put, when we think of from thin airfoil theory, we know that CL equals CL alpha times alpha minus alpha L0. I'm actually going to put a minus sign in front of that. So we're going to put a minus there instead of a plus. And so if you now solve for alpha L0, what we get is that's equal to minus tangent, the arctangent of eta naught over the square root of r squared minus eta naught squared. Okay, so that's our zero lift angle of attack. So what we've done is we've kind of manipulated this just a little bit, and what we see is that if we were to plot the lift as a function of angle of attack, so CL, it's not exactly linear. So we get a sine alpha in here, and we have a cosine alpha over here. And so this isn't exactly linear. From thin airfoil theory, we estimate that the lift is directly proportional to alpha and offset by this alpha L0. But what we're going to get, so from thin airfoil theory, we would get something like this straight line here. But what we're going to find is that line is curved ever so slightly. And curved so slightly that you might not even be able to tell it wasn't a straight line unless you put a straight line on the plot just to compare against. But so I'm kind of exaggerating the curvature here, but you get the idea that actually what we're coming up with here is that this is a function of sine alpha, not just directly proportional to alpha. So really this lift slope out front is just the lift slope at really small angles of attack. It's actually the lift slope here, here as where alpha is close to 0. So if we were to do the small angle approximation, we'd get an alpha in this term and a 1 here, and then a small angle in alpha L0. Then what we would end up with is this expression up here, and this is just a small angle approximation of this expression here. And that lift slope is from thin airfoil theory, we just have a constant out here, which we have here as well, but that lift slope actually changes as a function of alpha because we have sine alpha inside of here. So this is really the lift slope just for small angles of attack if we use a small angle approximation here. So anyway, that's what we get for a lift, and now we'll look at pitching moment.